Thank you for getting settled so quickly. The change in atmosphere in this room between when you came in and when I announced that our very special guest was here, I think demonstrates what a unique opportunity we have this morning. We take a lot of things for granted and we have access in our lives to many special things, but we don't always have such access to very special people. And that's the purpose of these Bridges lectures, is to give us amazing opportunities to interact with and hear from people who've made very significant differences in the world. I would like to, just before we introduce our very special guest, to welcome students from Leidner School. We're very, very happy to have you here today. We hope to be able to welcome you to some other events in the school soon. We also will have, I think, delayed in traffic at some students from the International School of Bangkok who are going to arrive very soon, and they'll be coming in the back door. So it's a nice connection between schools and international schools, just as the Bridges is a connection between very special people and real people. So I'd like to invite Isaac Lim, please, to come and introduce our guest speaker today.
Fellow teachers and classmates, as well-rounded scholars and seekers of knowledge, it has now become quite second nature to most of us to discuss the work of famous scientists, respected poets, and historical figures purely out of a textbook. However, how often are we given an opportunity, such as we are today, to get to meet in person one of the most influential physicists, one of the most prominent particle theorists in all of this modern day? Professor Gerardus Hooft from the Netherlands earned his doctorate in physics at Utrecht University in 1972 and became a professor there 5 years later. He shared the 1999 highly prestigious Nobel Prize in Physics with Martinus Veltman for elucidating the quantum structure of electroweak interactions. Professor Hooft was also awarded the Wolf Prize in 1981 and the Lorentz Medal in 1986. Furthermore, as is every young aspiring physicist's dream, asteroid 9491 Hooft is named in his honor. Professor Hooft is most widely known for his remarkable achievements in the area of quantum field theory and quantum gravity. In the realms of the Standard Model, he proved that gauge theories are renormalizable and developed the Hooft interaction of fermions. In collaboration with Leonard Susskind, he developed the resolution of Stephen Hawking's black hole information paradox. The holographic principle now provides a precise mathematical formulation within string theory, which demonstrates that the description of all objects which fall into a black hole is entirely contained in surface fluctuations of the event horizon. We are extremely fortunate today to have the professor talk to us about the education and collaboration of fundamental science as bridges between nations. It is hence with the greatest honor that I now hand over the podium to Professor Gerardus Hooft. Thank you.
Well, boys and girls, ladies and gentlemen, it is my pleasure, it's a great pleasure to be here, and I want to show to you that even though I'm introduced as a very special person, I'm also a real one with real ambitions and real ideas. And let me just tell you how it happened that I became the person I am, and that I earned this prestigious prize, as you know. Already from fairly early age on, I remember always being fascinated by things in nature. Things in nature were much more interesting to me than laws that had been invented by people. I thought people were ununderstandable to me, but nature was something you could really understand. And I developed that curiosity about nature already when I was a little child, and I was given a little bicycle with 3 wheels, we call them a bicycle with 3 wheels, and I was so fascinated by the fact that if something is on wheels, it moves very smoothly over the ground, whereas if you have no wheels, it's very hard to drag something along. So what makes a wheel so special? And I remember then that also wheels are a man-made invention. Someone has been very, very smart. Because animals have no wheels, and they have to walk. And without wheels, you have to walk over them. That goes slow and requires lots of effort. Because wheels go so smoothly. You push a little thing, and then it goes a long way. So I remember I was very envious. Someone has invented the wheel. I would like to have met that person. But it was long before I lived, I realized that. Because wheels were everywhere. And then I discovered something else. While all the other kids were playing on the playground with football or something, I saw that 2 children's bicycles were lying there upside down with their wheels free, but the wheels were touching each other. So if you were rotating one wheel, the other wheel would automatically rotate in the other direction. And if you touch a small wheel with a big wheel, then the small wheel will go very fast and the big wheel will be going very slowly, but also they transmit their one motion, one wheel is transmitted to the other wheel. And I realized this was a way to transmit motion from one system to another system. So I discovered this is the way how people make wheels go very fast. You can if you put several of these in succession, you would have the acceleration device. So I was very fascinated by this, and I was just curious that other kids were not interested. And okay, then we go on a few years, and I was at primary school and secondary school, and I was dreaming about becoming an astronaut, about going into outer space. I mean, who doesn't? It's so fascinating to see that, in principle, if you have the right kind of spaceship, you can leave the Earth and go to the planets and the stars and investigate regions of the universe that never anybody has been seen, has been active today. Only very few people have landed on the moon, that's what it was. When I was a kid, nobody had ever landed on the moon, nobody had left the Earth yet. So it was just a fascinating speculation. What would happen if someone would go in a spaceship and go out to Earth? This was all fantasy in those days. So I wanted to become an astronaut, and I realized, well, if you're an astronaut, you need a spaceship. So I wanted to build my own spaceship. And, well, a spaceship requires, essential things. First of all, you have to get off the ground, and then when you're out in space, you have to have a very strong hull to keep the air in, and so on. So I started to imagine how that should be made. But to go off the ground, you need to do something against the gravitational field, the gravitational force that keeps you back on the floor. So how do you get something off the ground? Well, someone had already invented the airplane, but that can never leave the Earth, because the airplane needs air to stay afloat. So you want something else. What is that? Well, I realized that to do that right, well, it was known that there were rockets, so you blast enormous amounts of gas downward, and then your spaceship goes up. But that sounds so wasteful. Aren't there better ways to screen away the gravitational force somehow? Well, I realized if you want to address your problem that way, you have to be a physicist. You have to understand the laws of nature. And I already understood some laws of nature. I understood how a wheel works, and I understood that if you take something, you drop it, it falls. You drop it, it falls to the ground. So those are laws of nature. Now, in order to make a device that goes up in the air, you need to understand the laws of nature a bit better. You need to be an Einstein. And in my days, Einstein was still alive when I was a little kid, and it was very intriguing that by pure thought you could make things happen that nobody else would have imagined before. The atomic bomb had exploded, and miraculous other devices had been thought of. The television was soon to come. When I was a little kid, there was practically no television yet, but it was being invented. It soon emerged in the first households. And so it was clear that if you understand the laws of nature, if you are a physicist, you might be able to build such devices and make new discoveries, make new inventions. I wanted then to become a physicist, so I could invent my own spaceship. Well, if you are a physicist, you have to do two things. You have to do experiments, but if you look at Einstein didn't make any experiments, he was just thinking. And by thinking very deeply, you can discover things. So I want to become a theoretical physicist, a physicist who understands things by pure thought. This is also an extreme sort of wisdom, and I would like to become someone like that, to think about the laws of nature very deeply and discover new things. Well, if you want to know how gravity works in every little piece of matter, no matter how small. And it is known in my days there are enormous forces inside the atom. Particularly the nucleus of the atom contains nuclear forces, which are very, very strong. And so things can happen there which are beyond the imagination. And to that one has to add that when I was still a kid, there were very many great mysteries in the nucleus of the atom. Things were not properly understood. So I want to become a theoretical physicist who investigates the nucleus of the atom, because the big secrets are there and should figure them out. Now, I was in a very fortunate situation, and this doesn't happen very often, but I had an uncle of mine who was a theoretical physicist, and whom I could ask any question I like. He would frequently visit my family, and whenever he visited, I would try to pull him in the corner and ask him questions about physics. And he was very good at that, at answering a question, because usually when I asked him a question, his response was, "Why do you want to know?" He didn't answer the question. He was questioning the question and asking counter questions. "Why do you want to know?" "Well, I want to make my spaceship." "Well, you can't do it that way." And and on it went in discussions. And gradually, I became more and more familiar with what was understood about the laws of nature, and I started to understand more and more. I also realized when you are a theoretical physicist, you have to learn to speak the language of nature, and the language of nature is mathematics. You have to understand the law of mathematics if you want to understand the laws of nature. And I was already good at mathematics, but I became even better because I loved mathematics. Mathematics is the language. If you understand how to do calculations, you might be able to figure out how things work. So I liked physics and mathematics. There was someone around me who I could ask questions, but usually didn't answer my questions. He said, the things you really want to know are far too complicated to explain. What you have to do is go to high school and then go to university. And I asked, well, which high school system should I follow? And he said, well, take a simple high school because you want to go to university as fast as possible. But in my time, there was a choice. There was the regular high school, and there was what was called gymnasium, where you also learned Greek and Latin. So I said, should I also learn Greek and Latin? He said, no, those things are good for nothing. But then I said, well, they are being taught. It's a challenge. I want to take all challenges there were. So I took the most difficult school system, including Greek and Latin, just because I didn't want to leave it there alone without even trying to learn those things. So, yes, I learned Greek and Latin at school, and eventually I went to university, and now I want to learn the real thing. Now, this time, my uncle was at the stage that he didn't like particle physics so much. He didn't like the physics of the atomic nucleus. He had worked on the subject himself. But he said people in that topic are so aggressive, and they claim things which they cannot really substantiate, and I want to be very precise and methodical. And he went into another branch of physics, which didn't catch my imagination so much. But there was another person at our university who was teaching the theoretical physics of elementary particles, the very tiniest particles inside the atomic nucleus. And his name was Martinus Veldman. He was quite a character, very, very different from my uncle. A strong ego, you would say that, but very easy. He was, very different, but he was also very smart. And I could learn a lot of things from him. And then, eventually time came that I wanted to work on a thesis. Because as a student, you first learn regular things, eventually you reach the stage But you have to do your own research, and that is being judged. And when your own research, which you can publish in a regular professional journal of science, then you can earn your doctor's degree. So he explained to me that he himself was working on a very difficult problem that he was unable to solve. But he said, that problem is too difficult for you, I'll give you something else to work on. Well, that wasn't the way to tell me what to do. Because, or maybe it was the way to tell me what to do. His problem was far more interesting than all the other things he wanted to burden me with. So I said, okay, fine, I'm going to work on your problem. Because if you can't solve it, maybe I can. And now, of course, he was far ahead. He had worked on this problem for many years. But I came as a newcomer. But I had my own ideas. And then we discovered that actually his ideas, in combination with my own efforts, we suddenly discovered that a very difficult problem that he was coping with could be solved. And this was a big moment in both of our lives, that we discovered that we knew something that absolutely nobody else on this earth knew, which is how to deal with subatomic particles in a systematic, regular way, in such a way you can actually do computations. Because that hadn't been achieved before. There were many theories for these very tiny particles, but we couldn't do accurate calculations. One could do approximate calculations, and there were all sorts of things known about these particles. It was known which symmetric patterns they form, we call it symmetry, and many of these symmetric features were known. It was known roughly in what way they interact, but it was not known how to compute accurately how these particles behave when they come close to each other, because their behavior appeared to be beyond our understanding. That problem could be solved. Actually, we solved much more. What we found was there's a whole class of theories, and very many different theories of nature you could think up with, all of which would allow us to compute the properties of the particles. And it turned out that all these theories had already been published by 3 other physicists in the United States, called Leidner, Glashow, and Salam. Salam was in Pakistan and India, but Glashow and Leidner were 2 American physicists. And they had already published a model which turned out to be exactly of the kind that we could now prove allow calculations. But those physicists did not know how to do the calculations, but they had a good idea about the model. So the discovery was that this was a model in which you can now do accurate calculations, and when this became known, suddenly a large number of physicists started to do new experiments to investigate this particular feature, whether or not this model describes reality. It was discovered that the model does describe reality in fantastic detail, and so the Nobel Prize went to those 3 people, Glashow, Leidner, and Salam, because they had proposed the first model, and that model works. So taking my advice, I felt very angry, because now we discover something and no prize goes to those guys. But well, that's life. And actually, those 3 people became my friends. I never blamed them for discovering something that they were not supposed to discover. So, so I was happy with the situation, and I was glad to play a part in the whole thing. Eventually, in 1999, it was discovered not only that this model worked, but also it was, we discovered in the meantime, also the detailed calculations are correct, because it was possible to predict new particles using exactly those calculations. And the Nobel Committee then decided that was sufficient for granting Velkom and me, this time, the Nobel Prize. So this is very much in a nutshell, well, my life as a physicist, as I would like to tell it to you. And I think now time comes to have just a dispute. I would love to have questions fired at me of all sorts and try to go to some sort of discussion. So if that can be done, then I'm really pleased. Thank you.
there was an interesting piece there where you almost described research as like a competitive sport. You know, you said, of course you're not disappointed if other people make discoveries before you, but there's obviously something that motivates scientists, this kind of race of things. Where do you think your core motivation to keep trying to make sense of this? Is it a mixture of competition, cooperation, and your own inquiry? How does it work?
That is absolutely right. I mean, I explained, in a very brief way, my motivation to become a physicist. That motivation was curiosity. I wanted to investigate things. I wanted to do things with it. So I wanted to do a kind of science that could eventually be applied to make spaceships, right? But I did not make spaceships. I discovered, of course, that making spaceships is far too difficult for one person to do, and it's not the way it goes. I did not succeed in making a spaceship, but I also realized that laws of nature are essential for that, and so on. So my primary drive was curiosity, and of course the will to make a difference, to do something, to discover new things that nobody had discovered before about nature. And so the ultimate goal of making a spaceship was not yet achieved. Actually, I planned to add something which I forgot, which was that a few years ago I decided to go back to this original motivation of building spaceships, and I wrote a book about the science of the future. Will it ever be possible for people to live on the moon, to travel to Mars, or to other distant places in our universe, and similar features of new ideas of science? Where will science lead us in a more general sense? It's a book which I've written. It is recently translated into English, actually by my daughter, and next week the book will officially be launched in Singapore. And it's called Playing with Planets. So I'm back to my original dreams. So those dreams were part of my motivation, right? And then come two other things, which is you want to accomplish something, you want to be part of the new discovery, and you discover as a scientist, all scientists are making contributions to science of some sort or other. You always make some sort of discovery, and being there when a discovery is made, no matter how small the discovery is, it is exciting and it makes life worthwhile as a scientist. So many, many scientists make small discoveries. If you add all those small discoveries up, you get something much, much more than the few discoveries made by the Nobel Prize winners. So the vast bulk of science is made by non-Nobel Prize winners, and a very, very tiny fraction of that is what the Nobel Prize winner has done. So, so of course, the primary motivation is being there when a discovery is made, and you want to make the discovery yourself. There is, of course, a competitive element in science, and it's a very important one. In a sense, it's a little bit like the Olympic Games, when you have all the athletes competing to be the best. And the best ones get medals and in the limelight, and visit the Queen and so on. And if you're second or third, I'm sorry, but you didn't win that medal. Well, second, third, yes, but then later, no. And science is a little bit like that. We like to be on the winning side of an investigation. So, but the Nobel Prizes are part of our discoveries, which just happen to be big ones. You never know it in advance. When you are a scientist, you see there is this huge problem that all the scientists are very much interested in, but you realize that a single person cannot solve the huge problem that we all see in front of us. What we can do is try to split the problem apart into very little problems, and realize that a tiny contribution to solve a big problem can be given by looking at a very, very tiny little piece of that and trying to solve that. So that is what most scientists in the world do, and that's what makes it all work. Because eventually then, someone is closing the gap, and whoever manages to put the cap down, to solve the problem now entirely, that person then is in the lucky position to get the Nobel Prize, at least athlete number one. But that may or may not happen occasionally. So the prime motivation is this combination. Of course, humanity as a whole is extremely curious, so you also see it as your assignment to enhance human understanding of nature. So I think, yes, the answer to the question is all of these things. It's competition, it's a sport in a sense, trying to be the first to discover something new, but also the discovery itself, the pleasure of being there, and the feeling you get when you make a little step forward of science as a whole. Science is a completely human, collective exercise that we all do. Some other questions? Let's see.
Can I just ask, you're obviously being recognised for this particular discovery. Are there many other discoveries you've made that you haven't been recognised for, or is this just competition is going on all the time, and it can be regularly, or once a year, or once every 10 years, that something significant happens with those discoveries?
Discoveries are not such a regular phenomenon, but are irregular. You suddenly discover something or not. And
so are there other discoveries that you're made, significant discoveries you're made in your lifetime?
Again, I should say that the Nobel Prize is the only prize in science that gets a lot of public attention. There are other prizes. So if you make another discovery which was not recognized in Stockholm, but it is recognized by your peers and by your fellow scientists, then yes, you'll be recognized for that as well. So many more scientists make many more discoveries, and it all goes in the books. So there's scientific literature, and in the literature, whenever a discovery is being discussed, the name of the scientist who made the discovery is there. So yes, I discovered other things. It was mentioned here in my introduction. Those are not the things recognized in Stockholm, but they are recognized by my colleagues. And similarly, I have very many colleagues and friends in science who make discoveries of some sort or other, and we recognize that. Whenever we mention a discovery or someone elaborates on a particular discovery, the name of the original guy who made the original observation is mentioned. And that is, in a sense, a reward already. A reward is not Stockholm, but still it is a reward. And I think it's very important to add that that's what these scientists work for. It would be wrong to do science only because you want to get this Nobel Prize. It's a recognition, but you're very happy when you get it. But if you don't get this Nobel Prize, but you did make discoveries are recognized by your fellow scientists, and that is a very rewarding thing that happens in your life. And we cherish that, even though it was not recognized by Stockholm, because there's only so few prizes that we give. The total bulk of science is much bigger, and many people contribute in an important way, and their names are all known and recognized. Of course, I should add, sometimes things go wrong. Sometimes the wrong name is added to a discovery, and people will then later try to correct it. So that's sometimes fights going on as to who actually was the first to make a certain observation or discovery. So that happens occasionally. We try to keep the record as clean and straight as possible, but of course inevitably mistakes are being made. And so it's like an athlete winning by just a little margin a certain race, but he has been cheating at the start, something like that. I mean, these things happen in science like everywhere else when humans are together.
Just going back to the idea of dialogue towards cultural peace, you have written a constitution for the future inhabitants of your asteroid. Could you elaborate on what the constitution consists of?
Yes, I should add that the asteroid is only a rock of a few kilometers in size, and the writing a constitution for its future inhabitants was inspired when I noticed that the discoverers of the asteroid had proposed to give my name to it. They are a Dutch couple of astronomers who, basically as a hobby, but also as a vocation, They studied photographic plates from Mount Palomar and other big telescopes and investigate and search for asteroids. They found a few dozen asteroids. And in astronomy, the rule is that someone who discovers something has the right to propose a name for it. But there are also the rules for the names. You can't just do anything. But asteroids should be named after persons. And so the couple decided that Welcome and me were next in line to have an asteroid named after us. And that happened. But the asteroid named after me was called Hooft without the apostrophe. And I thought, what a pity, where is my apostrophe? So I thought I should react some way. So then I decided to say, okay, there's going to be a constitution. All the future inhabitants of the asteroid have to live in agreement with the constitution. One important article in the Constitution is that asteroids apostrophes on the asteroids are forbidden. So anybody who enters, who lands on the asteroid and happens to have a notebook computer in his luggage, if that computer has a key with an apostrophe on it, that key should be removed because the apostrophe in the asteroid is forbidden. And so, and then I added a couple of other articles, because once you're at it, you discover other things like bureaucracy. We are annoyed that when we invite foreign students at our university, we have to undergo a tremendous amount of bureaucracy. And when they come from faraway countries, the bureaucracy gets worse. So one other article is that the amount of bureaucracy anybody encounters who asks for a visa to live on my asteroid should be at most half of the bureaucracy that foreign students have to cope with when they apply to be a student at the University of Utrecht. So that is another article. And okay, we can go on in this general study. Now I see more questions coming, also there. Is there someone who can perhaps point or list who asked questions?
Yeah, I'm sure you've heard of the Large Hadron Collider in France and Switzerland. Have you participated in the design or creation of it, and can its results, I know that they don't have the results yet, but might they be able to further your research or your findings?
I'm very happy that you mentioned the Large Hadron Collider. CERN CERN is a laboratory, if someone doesn't know, it's a laboratory in Geneva, Switzerland. There's a big laboratory for elementary particles. It is one of the biggest of the world, and when I was doing my work on gauge theory, I often visited CERN because that's where the prime experiments were being done. At the time, there were several other big laboratories, notably in the United States, in Italy, in Japan, where also big machines were accelerating particles to investigate their properties, and CERN was just one of them. Today, it so happens that a new machine has been completed, which makes CERN the top laboratory of this kind in the world. Even the Americans don't have a machine anywhere close to the LHC. Unfortunately, LHC is not yet operative. There was recently a technical problem which set the scheme back for several months because there had been an explosion which was fortunately didn't cause any human casualties, but it was quite a bit of material damage. It has to be repaired, and we're working on that now. But then, when that is completed, in a few months' time, the first particles will be accelerated and experiments will be done. One of the things they want to do is to detect one single particle that is, in all our models of elementary particle physics, this particle is there. It's called the Higgs particle. The Higgs particle is there to give the other particles not only their mass but also their other properties. It makes them distinguishable from other particles. So without the Higgs particle, we couldn't have the model work in all ways. So the Higgs particle is an essential ingredient, but has never yet been literally observed in machines. It's too difficult to observe this particle. Well, LHC is in the right position to detect this particle. It will be nearly inevitable that the particle will be found by LHC. And we all expect it to exist, but we don't know exactly what its properties are. In particular, its own mass is difficult to calculate from what we know now. So LHC will detect this particle very likely and measure its mass, and that will be a very important piece of information. Besides this, LHC will quite likely discover other things as well. It's opening a new terrain in particle physics, a terrain where we have many uncertainties about what's going on there. When I mention terrain, what I really mean is that structures of smaller sizes than ever has been detected before will be relevant for the behavior of particles under those conditions. LHC will collide particles with tremendous energy. The energy is more than all the previous machines. And one can calculate that in that case, the properties of the particles which are relevant to determine their behavior will be tinier structures in these particles than in the other machines. And so we want to know more about the tiniest grainy structure of these subatomic particles. And that is what LHC will reveal to us. And one way or other, new discoveries will be made there, and we're all very excited about the next 10 years. During a period of 10 years, the major discoveries will be made. After, perhaps the machine will work another 10 years to set the details straight, and then it will be finished. But that's, it's a world, well, practically a world accelerator, many different nations all over the world are participating. It's very large. It's a tunnel underground with a total length of over 26 kilometers. And in that tunnel, particles will be accelerated by gigantic magnets and other machines. And this is a very costly affair, but it's all within the budget of all the nations together united to have this whole thing work. So then the question, of course, what's my relation to that? Well, for my theories, it's extremely important that these observations are being done, but it's an extremely technical undertaking. And it's really technicians who make the machine. It is experimental physicists. Remember I said I was a theoretical physicist, but it's experimental physicists. We set up the experiments, the very delicate and complicated computer analysis has to be done. This LHC will have millions of collisions take place every second in this machine. And there are so many, every single collision will give thousands of particles. So billions and billions of particles are produced every second, far more than they can register. So it has to be decided on the spot which of these collisions are interesting, which aren't. And we keep only the interesting ones. So every second, 100 or so interesting collisions will be registered in the computer in all full detail, and then the data will be examined. A very, very complicated procedure to perform. It's not my work, so it are other colleagues in physics who have dedicated their lives to make such a machine work. Very, very interesting, but very, very difficult and technical. And it's, again, one of those high challenges humanity is facing, trying to make such a machine and make the machine work properly.
Excuse me, sir. As you mentioned before, when you were doing your thesis with Professor Veltman, when he mentioned to you about his research he's doing and you took up the challenge, during that time, of course, Professor Veltman would be definitely far more experienced and did a lot more research throughout the past few years. How do you keep up collaborating with a person with far experience and end up managing to assist him?
Well, you have to realize that every scientist is facing the same problem. When you are a young student, you can't possibly know everything has been done in that field. And most of that research is far too complicated. You don't even understand what's going on. So we all face the same problem. And then those guys who manage a coping situation the best will then be able to complete that kind of research. So indeed, there were decades of research had been done when I entered the subject. And much of that research was fast to even to comprehend. But sometimes that's an advantage. You start with knowing much more than those other people knew when they started their work. So those investigators had less access to modern data, of course, than the later ones. So I entered the subject in a more favorable circumstance than Veldman, who entered the subject basically 15 years earlier, and other colleagues who, by age, were earlier than that. The understanding of nature was much less complete in those days. So I had that advantage, that it was known what to do and what not to do in more detail than it was known before. Although there were still many mysteries, things which didn't fit, didn't work. So sometimes not knowing all those blind alleys that people have been trying before is an advantage. Because sometimes science is trying everything, and you're in the forest. And all the different pathways, they lead to nothing. You try them, and you find there's a blind wall at the end of this alley you didn't know before. You have to go back and try something else. And every now and then someone succeeds and discovers there's a pathway to obtain better knowledge. So when I started, those were better known than the earlier scientists knew. So I had that advantage. And if you do science, that advantage is enough to help you along where others before you failed. Not because they were scientists, but because now the situation is better because of the new knowledge that has been obtained in recent years. So I was in that position. There are many things I did not know, and sometimes ignorance is a blessing. There were many things, there were many reasons why people in those days did not believe quantum field theory to be correct. I did not know why they believed that quantum theory was incorrect. It turned out later that there were various reasons why people thought quantum theory can't work. All those reasons turned out to be wrong. They were misguided. But they couldn't have known them. The only thing, both in the Soviet Union of those days, Russia was the Soviet Union then, and in the United States in particular, and in Europe, groups of people all had reached the conclusion that quantum field theory doesn't work. They had different arguments, but they all agreed. So they said, oh yes, of course, we know that. Quantum theory doesn't work, don't do it. I didn't know their arguments. They were wrong. And, but all three of them had different arguments, which were all wrong, why quantum field theory doesn't work. And I just started doing quantum field theory. I liked it. This was the way to do it. It seemed to me, and I couldn't understand why other people were not doing it. Well, they listened to those guys, or old guys who said the theory doesn't work. So I had also ignorance is sometimes an advantage. If I had known, if I had totally understood the arguments why quantum theory doesn't work, I might never have entered to do quantum field theory. But I didn't know that. So I just thought this is the best way to do things. And there you are, I discovered that the arguments were based on misconceptions. And now we made progress.
Sorry. It says in the pamphlet that you're a proponent of permanent. Sorry.
Oh, yes.
It says in the pamphlet that you're a proponent of a permanent human presence on the moon. And personally, I love the idea, but do you think you could ever be really anything more than a symbolic presence?
Well, I find it difficult to believe why not. I mean, the moon is, of course, a very hostile environment, but not as hostile as, say, Antarctica or so, where you find no resources whatsoever, only ice. Where on the moon, all the minerals are there, so you could harvest also different minerals to build structures, and you have plenty of solar energy available. There is no atmosphere, and that's the problem. So you have to make your own habitat, so to speak, so you can only live in closed areas where you somehow made a roof of glass or something like that to live under, to have air, and then you have to bring water there. That is a problem. But once you have that, you could inhabit the entire moon, and so you would make a big village, or rather a rather sizable human habitat on the moon. And I don't see why that couldn't happen. But the problem could be motivation. What do you want to do there? How do you think life's interesting there? I think it is. One reason is very low gravity there, so we have a very different gravitational field than on Earth, and that might be very interesting because that opens up possibilities in life that normally you don't have, like man-powered flight. It should be relatively easy for them to fly around, just because you don't weigh so much, and people like this, things like this. So, so life on the moon could be very interesting in some ways, and it's worthwhile to investigate the possibilities. And also as a challenge, I think humanity shouldn't leave any challenge unaddressed. So if there is a challenge here, we should try to face it, and let's see what we can do.
What sort of lifestyle can you expect if you do pursue the path of a particle physicist? For example, do you have any...
Can you raise your hand when you talk about it? You talking?
Yeah.
Okay.
So what sort of lifestyle can you expect if you do pursue the life of a particle physicist? For example, do you have any interests outside the field of physics? Because as it seems nowadays that most scientists, science consumes a large part of their life.
Well, I have lots of interests besides physics. When I was at school, my art teacher said you have to go into art. I had a piano teacher said you have to go into music. So I like art, so painting and music. There are other things. I like to collect shells along the beach. So I have other interests, and I like to read stories of all kinds. There is of course science fiction. But also serious books or novels or whatever. So yes, as a scientist you have many other interests, and I should add to that scientists are as diverse a group of people as anywhere else. I mean, if you're an athlete and you're interested in ice skating or in ballet or perhaps if you're a musician interested in performing, these people also are all different, and many of them have other interests as well, not just the field that they want to excel in, but in many other fields as well. But it depends, it's a very personal question, it depends very much on who you are and who you want to be and how you want to spend your life. And the answer is as complex and as diverse as in other fields of human activities. So yes, the answer is many scientists have other interests. Only very few of them are so monomanic that they are only interested in one thing and absolutely nothing else. But there are not so many people like that.
Excuse me.
I'd just like to ask you, after you received the Nobel Prize, did you sort of feel like you completed the research that you set out to achieve and then you could focus on things that you previously investigated, or are you still going on to new things? And if so, what's your primary research right now?
Okay, for most Nobel laureates, receiving this prize doesn't mean that finishes your research, because as I emphasized earlier, that the Nobel Prize is not the aim or the motivation for your work. So I am very strongly motivated to continue, and I want to understand things better. Right now I'm investigating a big mystery that some of us feel to be more mysterious than others, but the basic laws that control the behavior of the tiniest particles is formulated in a mathematical language called quantum mechanics. Now, quantum mechanics tells you that the response of particles to forces acting on them is very different from in the ordinary world. Planets obey a force law that go around the sun, which is very similar to the force law that electrons feel when they go around the atoms, the nucleus of an atom. Yet electrons going around the nucleus of an atom behave very, very differently from planets going around the sun. The reason is that electrons are controlled by quantum mechanics, whereas planets behave according to what we call classical mechanics. Now, the big difficulty about quantum mechanics is what the theory actually tells you that about reality. It tells you that an electron can be here and here at the same time. But what does that mean? And you only detect the electron either it's here or it's there. But when you do your computations, you do as if the electron can be here and here at the same time. And that's very confusing and for some of us very unsatisfactory. There's something wrong about the theory. And I happen to believe, yes, there's something wrong about the theory, which really means that this electron, the thing we call electron, is not really telling you what's going on in the atom. There is something else. And the big question is what? And how do you phrase this properly? Now, this question has been around from the very beginning of quantum mechanics. So in 1926 or so, Schrödinger wrote down the first equations for quantum mechanics, which turned out to reveal in mathematical detail how to work with quantum mechanics. And after that, people realized this is the way to work with quantum mechanics. We understand mathematical description, we understand how to compute anything you want to compute, but we don't understand what the theory really says, what it says about reality. And I happen to think that's important because there are mysteries which we haven't solved, which is what happens to the subatomic particles at distance scales much, much shorter than what we can reveal now in particle accelerators. There's some problem if you go to the smallest distance scales that you don't understand. Perhaps this problem has something to do with the nature of quantum mechanics and what quantum mechanics really tells you about reality. Now, this is one of my main present interests, besides my present interest about black holes. A black hole is an extreme form of, well, you could call it matter, you could call it gravity, you can name it anything you like, but you know how to describe mathematically a black hole. But in combination with quantum mechanics, the thing starts to behave in a very mysterious manner. And there are many questions to be asked there as well. And it's those questions which I'm also very much interested in today. So, yes, research continue, and no Nobel Prize doesn't mean that to this point and not further. No, we just continue.
What are your thoughts on string theory?
String theory is a very interesting approach, and it's the idea, for those who don't know, that particles at very, very tiny distances, this is way tinier than one can disclose under experimental conditions. Particles are no longer point-like, but are like little piece of thread, strings, which vibrate and rotate in complicated ways. Now, this theory has very remarkable properties, and one of them is that it seems to explain why the forces are the kind they are and why there is a gravitational force. And all this made people suspect that string theory is the answer to many of our questions, including perhaps the question I just mentioned before, for black holes or quantum mechanics. They've been saying that now for over 2 decades, and that string theory should be the answer to all these questions. But in contrast to the first ideas people had, it turned out to be not so simple. So string theory is an interesting mathematical idea. I've also been a bit opposed against what people put in their advertisements, which was that string theory was going to solve every question on physics that we have today. And I always maintained, I said that cannot be true, I don't believe that. And I still think that I'm right here, that string theory is not going to give you all the answers. That does not mean that string theory would not be an interesting theory by itself. It is very interesting, it's something worth studying, it's worth figuring out in what way string theory should describe these elementary particles, but there are many mysteries that have not been answered. I'm not very good at string theory because you need a special kind of mindset. Those people were extremely motivated because they thought string theory is going to solve all our problems. I wasn't that much motivated because I thought string theory is not going to solve our problems. I'm right in that, but in the meantime, there are people who got much further in string theory than I'll ever be able to do. So I let them continue string theory. Maybe they were right, but I think they were wrong, and that the ultimate truth is something more complex, but on the other hand, also more simple than string theory. String theory is mathematically a very complicated construct, and you need a lot of intuition to deal with that. I don't like theories where you need intuition to understand what the theory says. You need to have a very down-to-earth prescription, which every child will understand, and then the only thing the child will not be able to understand is mathematics, but the whole itself should be understandable. And string theory is not of that sort. Which is why I have no hesitation, big hesitations of string theory as the ultimate answer. However, string theory is a very mathematically interesting structure, and it deserves to be studied. So it's just being overemphasized a bit in the last few decades in particular. Now string theories have become a bit more modest because they realized that they have not been able to answer the question as promised. And they also realized that they will not be able to answer many questions the way the theory is now. The theory says that the world is, because if it wasn't like this, we wouldn't be here to see it. That's a very bad answer. Of course it's true, but if that's the complete answer, it's not the kind of answer physicists want to give. But if string theorists can only give this answer, we're not very happy. And we think it's not the answer to everything. We should find better answers. And I haven't given up hope that better answers will be found.
Yes.
Who's talking? Yes.
My question links to another person's question about your life outside of physics. And I understand that you get prize money when you receive a Nobel Prize. And what I've always wondered is, what do the Nobel Prize winners do with the prize money they get? And I would like to ask you, did you do anything particularly interesting with the prize money that you received?
No, I must confess I didn't do anything interesting with it. It just makes your life a lot easier when you have that kind of money on the bank. And right now, I think I'm paying for some of the houses of some American people who couldn't pay their mortgage. That's kind of but anyway, but otherwise, no, it just makes your life more comfortable. And that is what the prize originally was intended for. Nobel's own idea was that the prize should be 1 year's salary for the investigator, so that he or she can freely do research without any financial troubles. And so Nobel had this idea that the prize should be just for personal use, allowing someone not to worry about any financial problem while doing his research. And well, that certainly worked for me.
Yes. What are some practical uses of the research on quantum physics and particle physics, and what type of technologies could be developed by your research and discoveries?
That itself is a good and interesting question, because in the past, the question has often been asked. I heard that in the past, I think Faraday was asked, he was doing fancy experiments with electricity and magnetism, and nobody understood what that was good for. And when Faraday was asked the question, he said, I also don't know what it's good for, but I do know that once in the future taxes will be raised on this subject. And he was quite right in that. Now, I do not expect that taxes will be raised on some devices using subatomic particles. That's unlikely. The idea that this topic will have direct applications is rather far-fetched, and it's not the motivation for doing this. What we really want is we want to understand why the world works the way it works. And it's that understanding which is our prime motivation. But understanding things also always turns out to have useful applications. Perhaps not in the field of particle physics itself, but somewhere else. For instance, particle physicists have to face extreme challenges in order to do the experiments they want to do. They have to make extremely strong, extremely accurate magnets. They have to make extremely fast computers, and they have to make an extremely complex infrastructure to distribute all the data to investigate those. Also, the scientific exercises we are doing, the research, is a very international research. People from all over the planet are united in trying to answer those questions. So, facing those questions, trying to have all noses in the same direction, trying to solve these problems, is a very powerful agent for generating peace. So you could say that having a peaceful collaboration between very many people from different nations itself is an important application. Now, it also turns out often as side effects you get useful applications. Even, the famous example that space travel had application because the Teflon pan came out of attempts to make better hulls for spacecraft. Understanding has applications. For instance, several of my graduate students, after they got their PhD in particle physics or cosmology or God knows what, they went on to do as a career in banking or in insurance companies or whatever, and discovered that the skill they developed is very useful in solving problems. So the capacity of problem solving, our ability to phrase more accurately what a problem is and what kind of mathematics you need to solve it, that itself is a very important ability that we develop doing this kind of science. So eventually applications come along the way, but if you ask for direct applications, like other fields of sciences do have, for instance, nanotechnology will have vast numbers of useful applications in the computer industry or whatever. I can imagine many other biological sciences, for instance, genetic engineering. Those are sciences which have tremendous amount of applications. Particle physics is not like that, unfortunately. Nuclear physics is something else. The nucleus of an atom, when you have interaction among nuclei, that has tremendously important features that can be applied, say, in medicine, but also in energy generation. Medicine, by the way, also makes use of subatomic particles. The protons or neutrons can be used as a radiation source for investigating or for treating organs at a certain resolution. So there are applications of that sort, but not very plentiful, and probably not at those very, very extremely high energies that people use in accelerators. So, but there is really understanding that I consider as the best application. There are more questions?
Oh, can we take two more? We can take two more. I'm not the bad guy, I'm the good guy. Actually, we can take two more questions, so I'll go down again.
Can you point who's asked? There's someone here.
Yeah. When you were talking about quantum mechanics, you mentioned Schrödinger, and I've heard about his theory, the Schrödinger's cat. I never fully understood it. I think it's the same kind of thing with the electron being in two places. Can you explain it?
Yes, Schrödinger himself, who was at the very basis of writing our first correct equations for quantum mechanics, had difficulty when people expanded on the idea and said, well, it's a question of probabilities. Schrödinger said, I can't understand it, there's something wrong here. And he said, then he devised a Gedanken experiment. He said, suppose I have a closed box. In this box sits a cat. And in this box also sits a machine which has a decaying, a radioactive atom in it. And as soon as the atom decays, it will trigger another device, and the device will open up a bottle of poison and will kill the cat. If the atom does not decay, the cat will not be killed, the cat will be alive. Now, according to quantum mechanics, whether or not a particle decays is sometimes not absolute. The particle can be in a state where it is decayed or not decayed at the same time. Just like I said, the matter can be here and there at the same time. We can also have a particle which has decayed or not decayed at the same time, according to our way of describing quantum mechanics. But now here was a problem as Schrödinger saw it. If the particle has decayed or not decayed at the same time, it means that this cat here is dead and alive at the same time. How can that be? So he said, this is all nonsense. All these things people say about quantum mechanics must be nonsense. Later we realized that, yes, Schrödinger is right, it looks very strange, but yes, this is the way quantum mechanics works. And actually, this cat is not really dead and alive at the same time, but if the box is closed, we, as an outsider, outside the box, we don't know whether the cat is dead or alive. So, in our knowledge, in our way we refer to the cat may be dead, the cat may be alive, we don't know, because we don't know whether the atom actually has decayed or not. So in our mind, the cat is both dead and alive, because both possibilities are still there. And quantum mechanics is a very enigmatic theory describing things to be this and that at the same time. And but I can't explain things better than that at the moment, because to explain better you have to follow a year's course of quantum mechanics as a student at university, and another year to get advanced quantum mechanics, and many of them still don't understand. So it's a very tough question.
Here, I was just wondering. Here.
Yes. Okay.
I was just wondering if, you know, your invention or maybe your discovery, it's totally different from what we all believe right now. What are you going to do? Like, how are you going to influence people to believe, or kind of, you know, come up with your ideas to make a difference?
I can try to explain a little bit more what we did. It was known that particles undergo different kind of interactions, and the interactions were inferred from the properties that had been observed as particles. Particles can be observed using fancy machines, and particles by in the old days it left typically a trail of bubbles, and photographs of the bubbles were being made, and analyzing those photographs we could figure out how particles behave. And by doing this many times, you get some notion about how particles tend to behave. Now, we would like to be able to calculate that. So we want to calculate how many times this particle scatter this way or that way when they collide. The same question, you take two buckets of water, you throw them together, the water will splash and go this way, go that way. How will it splash? Can you calculate that? Well, people who know a lot about water will be able to calculate what happens if you throw one bucket of water in another bucket of water. How will it splash? It's complicated, but it can be done. And similar thing, particles, if two particles collide, lots of fragments will go in all directions. How will they behave? And it turned out that we knew the forces, at least to some extent. We knew other properties of the particles, such as their mass and their charge. So the assignment was, okay, you know everything about these particles, now compute what happens when they collide. And then the remarkable thing was that the rough calculation gave roughly the correct answers. So people could do rough calculations. Then they said, well, wait, do the rough calculations fine, but we want to do exact, precise calculations. So now we have a rough idea of what happens when the particles collide. Now make a correction. We say we do a next order calculation, which means correct all the sloppy intermediate results to get a more accurate calculation about what happens when particles collide. Again, you need to know how they interact and how they respond to the interaction. And much to people's surprise or envy, when you try to do calculation more accurate, the answer was the opposite of accurate. It was nonsensical. You calculated particles collide infinitely strongly or something like that, which is impossible. You can't get infinite out of an answer as an answer. So there's something basically wrong with the calculations if you try to do them more precisely. And then comes a lot of mathematics. So now the question was, why is it that you get this wrong answer? It turned out that the wrong answer was wrong because of the assumptions put in. The assumptions were that you knew what the mass of the particle was, you knew what the charge of the particle was, and then you got out this meaningless answer. But the correct answer was that also the interactions affect the mass and the charge of these particles. So the mass of the particles and the charge of the particles wasn't the actual value that we assumed they were infinite as well. So now you have two infinities. You have infinities, these particles gave infinite interactions. Well, what does infinite mean? Well, probabilities can't be infinite, so something wrong, something nonsensical with the answers. But also the masses, the correction to the masses were also infinite. Now we say, wait a minute, we don't turn things around. What we observe is the mass of the particle after the interaction took place. We observe the mass, the charge of the particle also after the interaction took place. Let's keep those fixed, and now do the calculation again. Well, this was a very hard assignment, because now you have to do two calculations at the same time as well. You have to compute the correction to the mass and the charge, and you have to compute the correction to all the other properties. Now, if you do all this in conjunction, and if you follow the exact right rules, then you get meaningful answers. This process was called renormalization. Renormalization means you have to renormalize the mass, renormalize the charge, renormalize some other properties of the particles. And if you do it correctly, and if you keep control of everything that happens, in particular your bookkeeping, then everything will come out finite. And this was, in a few words, what we did. But the exact statement is, words are good but not good enough here. You have to write down the mathematical equations. And this could not be done before we were writing down what the mathematical equations actually are, how can you make them work consistently, and how can you, with mathematical rigor, prescribe how to do calculations. And okay, there are many, I can go on for ages on this question, but I should stop here.
So now I am the bad guy. I'm unfortunately going to stop these question and answers. Thank you. I'd like to say thank you as an audience. Very interesting questions from all the schools here. I've very seriously exercised the left-hand side of my brain today. I think I need a rest. I need to go and look at some art or something to balance myself out. But what a fantastic opportunity, as I said. I was just scribbling down some thoughts as the professor was talking. First of all, can you put your hand up if you love maths as well? If you love mathematics. So you're in very good company today. It's nice to see our maths department putting their hands up as well. But I think there are some fascinating things for me, as a person who doesn't love maths, listening to a life of inquiry and understanding and making the connections between that. Some things that I'm taking away from listening to Professor Till's speech today. First of all, the idea that you can take on all challenges. You know, even talking as a student in his early days, taking on Greek and Latin, reminded me of the IB, you know, taking on things that you may not choose definitely to do, but you take on subjects that challenge you. The idea of this balance between collaboration and this striving, this competitive urge to be the best you can and discover something for the first time, but also building that based on other people's discoveries as well. That you can actually be trying to be the best, but also be collaborative at the same time. I think that applies to everyone in every situation. A sense of playfulness. You know, writing a constitution for your own asteroid. That leaves, ensures that nobody will ever use an apostrophe again. And I think heavy thinking and deep thinking doesn't have to be lack playfulness. And I think if we all maintain that in our lives, I think it makes things a lot easier and keeps our brains working and lubricated. Also the idea that hearing in a lifetime science fiction you become science fact, and that therefore dreams that we have and think are unattainable can actually come true. And whether or not that's through science, which many of you may choose as your direction, or whether it's through another vocation, things that we dream about that we don't think are possible now could come true in your lifetimes. And you're the people who are most likely to make that happen. And finally, the idea that the assignment of humanity is to be inquisitive and curious. That's what we're born. We're born to be interested and try to seek out these discoveries. And if one person in this room, in one field, takes that inquisitiveness and turns it into something real, and I apologise for not describing you as real at the beginning, then I think that's a success for everybody here. So, very inspired myself, and I hope that you're inspired to go out and find that area that is your area, the area that you're curious about. Look for the bicycle wheels spinning in your lives, and try to enjoy it while you're doing it. So for us at the International School, I'd like to say thank you in a very small token of our appreciation. I'd also like to I think Mr. Uwe Morovitz from the International Peace Foundation has also a small token you'd like to come up. And please stay put for a couple more minutes. We have one more task after this.